Hello, welcome to a video about lambda calculus. There's a lot to do, so let's get started. We'll ask right now, what is lambda? And it's an anonymous function, right? And a function without a name, so that's what it is, right? Calculus, what is calculus? It's not like differential or integral calculus, which is the most common one that people know about. It's just a way of calculating things, and it's a way of moving symbols on a page. What skills do you need to do lambda calculus? Well, this is it right here, right? Can you replace every W in the expression wow with an L? If you get this answer, LOL, then you can do lambda calculus. Okay. So I'm obviously someone who likes lambda calculus, otherwise I wouldn't be making a video about it. So I've actually gone through a couple of other lambda calculus videos before, just to see and take ideas from people. Just to take all the good parts and try to make one video of it and try to explain it in the best way. But so far that I've seen, this video right here from Full Stack Academy seems to be the best that I've seen so far. It's very, very thorough. It goes pretty advanced, but it's really thorough, and I really like how Gabriel Lebec, how he talks about all the stuff. So rather than spending like maybe another hour talking about like the fundamentals, introducing this stuff, I probably will just send you to watch his video. At least watch. Well, in the first half, in the end of the first half hour, he's talking about the history. That stuff is good too. But I think about half an hour in, you should know enough to be, maybe even after 20 minutes, you should know enough to be able to follow along with this video that you're watching right now. So yeah, I mean, at least do yourself a favor and try to watch this or some other videos about lambda calculus. Maybe read this paper, because this is how I learned from this paper. And because I'm gonna try to go like really fast, so I might just really briefly skim over stuff that is talked about. So okay, now that you're back from watching the videos, hopefully you did that and you know a little bit now. You probably have enough knowledge to reduce these problems right here. And if you didn't watch the video, well then I guess I'll just do my best to explain how I reduce this, right? So we want to look at this expression, right? It's really made of a bunch of terms, right? And these are the terms. It looks like there's 4 terms, right? And how we evaluate, right? I'm just gonna go ahead and be really thorough, redundant, right? If you watch the video, you probably don't need to know every single step of the reduction, but I'm gonna go ahead and say everything there is to say about it, right? So when we do the reductions in normal order reduction, we look at the leftmost term and we apply it to the rightmost term, right? The leftmost term is the function that we apply to the value that we see directly to the right of it. So how do we do that? Well, this function is going to be applied to z. So in the body of the function, the a is going to be replaced with z, and then it's removed from the head. So the next step down would look like this. And then here's the a being replaced with z. All right. So then it'll consume the z. Oh wait, this should be a z. Okay. And then the b will be replaced with z. Yep. And then we have that. And then next time around, c is actually going to be applied to the whole entire function right here, all this whole thing in parentheses, right? So we replace c with the entire thing, and we get rid of it in the head too. And since the head is gone, right, the head of the function has no more parameters, we just can get rid of the whole thing, and this is what we'll have. We can get rid of the parentheses on the outside; they're redundant, and then all we have to do next is apply this function with the wdb.w to z, and that's what we get. And then finally we apply it one more time, this function, right, lambda v dot z to z, and it just unconditionally throws away the argument and just gives you z, so the result will just be z. That's what you should get after doing this one. All right, we have a couple more to go. Here we have x being replaced with lambda a dot a, so that's what we'll do. And since the head is empty here, we could just remove it completely, replace x with lambda a dot a, and now this function all here, we could apply it to b, so we replace yy with b, and now we just do lambda a dot a to b, and we're left with bb, right, because we still have one on the outside, right? What we did here is we applied lambda a dot a to b. And so if you don't know what's going on, hopefully you're catching on and seeing that it's really just like one simple rule to transform and reduce. Right? Okay, so this one, lambda y dot y, the identity function applied to this lambda x dot x, just gonna kind of just make it go away, right? And then we have lambda x dot x applied to lambda z dot zq. We get two of those. Apply lambda z dot zq to itself, and we have z being replaced with the lambda z dot zq. That's the next step. And then after we apply that one more time, we just are left with qq. Alright, here we have this one, lambda z dot z applied to lambda zz, and then that just gets rid of it, right? This one gets applied to itself again, right? And we are left with that. And then again, yy. Actually, if you didn't notice, this one is actually alpha equivalent. It seems to be, yeah. Actually, these two, except for the q. The only thing that's different here is the q, right? That's a free variable. Maybe you should have learned about free variables by now. It's just a variable that's not the input of that function, right? So there's no q here in the head, so it's a free variable here. Just like the y is a free variable here. But everything else is pretty much the same, right? And so that's why we're getting these two, qq and yy, as the result. Alright, so lambda, so that we apply this one to y dot y, right? So we replace the x with lambda y dot y, and then we apply, well, really, when we apply this to y, we replace y with y, and then here we have lambda y dot y inside. We're reducing now here inside here, right? We apply this lambda y dot y to a y, and then the result is, whoops, I forgot to get rid of this right here, because when we apply this function to the y, it goes away in the head, right? When we apply a function to a value, it's like no longer a function, right? It's the result of whatever the function returns. So yeah, in this case the result is just yy, just like the last one. Alright, and then now this one, so we have lambda a dot a applied to lambda b dot ba, so we would just write two of them after that, and then we apply lambda b dot ba to itself, so we have b replaced with lambda b dot ba. Alright, and then lambda b dot ba gets applied to c, wait a sec. Yes, I had this backwards, right? Because once I'm looking at this, right? I apply this function to this value, and then this will be inserted into here, and so yeah, A and then C. Yeah. Okay. So then we apply this to A, and B will get replaced with A. So we'll see what that looks like, and the result will be AAC is what you should get. All right, next one. All right, let's look at this one. So notice right here we have lambda xyz dot xz applied to yz. We could have, all right, so what we're about to do is you see this right here, lambda x dot z, we're about to rename one of the z's because this z is not equal to this z. We could have done it over here with this one, right? I could have renamed probably this lambda y dot y to like lambda x dot x. To make it less confusing, but it wasn't really necessary, so I didn't do it. But this time it is necessary to replace. Hopefully you already know what alpha equivalence is because you saw the video. If not, I'm going to explain it really quick. It just means that this function right here, lambda x dot x, is the same thing as lambda z dot z, and it's the same thing as lambda c dot c. Right? It doesn't matter what you name the parameter. It's just a placeholder, right, for a real potential argument to take its place. So anyway, we want to know which one of these z's we want to replace. We actually want to replace this one, right? Because this function lambda xyz dot xz all applied to yz, it's the same, it's alpha equivalent to say this one where we apply this z with an s, right? It doesn't matter what we name the variable, it's just a placeholder, right? Whereas in this one, lambda x dot z, we don't know where the z came from, and so we can't really rename it. It's kind of like a random value, like it's kind of injected in there. It just makes sense, right? We cannot rename it, but we can rename this z right here. And so that's what we're going to do, right? Rename this to, I don't know, A. Doesn't matter what you rename it to. But the point is that after we did that, now we can apply it to this lambda x dot z. So that's what we're going to do. X is going to be replaced with the lambda. Alright. And now the next step would be applying still the outermost and the leftmost. So this one apply to this one, lambda x dot a. So y is going to be replaced with this lambda x dot a. And that will be right here. And okay, well, we can't do anything on the outside, but we can still go in the inside and reduce further. So that's what we'll do. Here we have we could reduce inside the body, right, which is everything after the dot, all this stuff I have selected. So lambda x dot z applied to a will just unconditionally throw away the argument and give you a z. And then we have this stuff. We have lambda x dot a applied to a, which is going to throw away this a and just give you the a in the inside, which I guess are the same a. And so now I think this is the result. I think this is the result. Let me just double check real quick. Not entirely sure. Let's go. Okay. Go here really quickly and we'll go to the answers of that. Okay. Okay, here's the problem. Here's why this confused me. Why I kind of had a bad feeling about this one. I know why. Here it is. So I renamed the z to become an a. And it turns out that's bad because this is an A right here and this mixes up later. So well, let's say I had no knowledge of that there's an A here. I will have to rename the A somewhere later on, right here probably in this step. So we'll just ignore all this stuff. And then here, well, we have this stuff applied to lambda x dot a, and this a is a free variable, this a is a bound variable. Let's rename it to a b. Now when we apply it, we don't have a mix of a's that are the same a, are different a's, right? The mix of the same variable that are different variables, right? So anyway, we replace y with the lambda, and we do the same steps as before, which apply this to b, we get z. Apply this to b, we get a. And so this is the result, the answer for it. This b can be anything, right? Because it's just a placeholder, it's just the parameter. It doesn't really matter what we name it. It is just going to be thrown away as soon as we apply it. And so this would be the result, b dot za. Parentheses there didn't matter, so I took it off. And here you can verify that the ones from before are also the right answers. And this one, see, z1.za, z1 just means that they renamed the z to be the z1. Yeah. So it allows them to distinguish two variables z that came from different places. All right. So hopefully you got these right. Now we can actually begin the real stuff, the real exercises from the video, which come from, so yes, the main theme from the video is going to be pause and try, right? I can't pause the video because the video has to keep going, right? Video, it can't go on forever, so I'm not going to pause the video. You pause the video. And yes, before every exercise that I'm about to show you the answer of, please pause and try it for yourself, because that's how you're going to get the most out of this video. So yeah, and if you want, read this entire paper right before, only like 9 pages. It should take you like an hour to read maybe. It just explains lambda calculus and stuff, and it gives you a lot of stuff that we can use. Like it's going to show you pretty much how you can do math, right? How you can have numbers, which are these things, right? These functions. How you can do things, right? How you can do addition, multiplication, conditionals, true and false. But we're about to implement all that, so we don't need to read it twice, right? We're pretty much going to do all that stuff, and we're going to do it while we do every single one of these questions. Define the less than and greater than of two. Yeah, we're gonna do all these questions. So let's jump right in. This is a lambda calculus evaluator that I made, and I made it so that these questions can be easier to do, but luckily it's online, so you should probably go on right now on your computer and go ahead and head on over to lambdacalceval.ronaldmcorona.now.sh, and well, we're gonna want to select this maximum overdrive thing really soon, but here you're gonna have this code in the very beginning, and you'll see that this and true will evaluate to true. You could see the reduction steps. So this is nice if you have any bug in your code or your lambda calculus code and you don't really know why it's going on. You can sometimes look through these reduction steps and kind of figure it out. But for now, we're going to turn it off because it's actually more efficient. So in order to do less than and greater than, we're going to need it to work with numbers and stuff and all this stuff, but we'll get there in a second. First of all, I'm just going to give you these two, which are the true and false, right? True and false values, they can be represented as functions that take two inputs, and true will give you the first one and false will give you the second one, right? Why are they like this? Because the basic observation that we have is that we use Booleans to select between two values. Right? So you know, like in an if statement, if you program, right, like you say if true, if 1 equals 1, then it's true. Then if not, well, maybe that example doesn't make any sense at all. It's stupid, but let me just show you how to use this, right? So here we have true xy, right? Xy are just some random variables with no meaning, but the point is that true, when you give it xy, it'll give you x. When you give it false, it'll give you y, right? Because, well, here we could look at the reduction steps. Hold on, let me toggle them on. Right, well, false is really equal to that function lambda a b dot a, and then a gets replaced with x, b gets replaced with y, and what we're left with in the body is the b, which gets replaced with y. So that makes sense. So now here's going to be the first task, right? The first useful function, not, right? It's gonna take in one input, right? And well, it's gonna probably be used in the body of the output, right? And it's probably gonna be in there somewhere in the result, right? But now we want to think about how we can get not true to evaluate to false, and how to get not false to evaluate to true, right? How can we make that happen? Well, we know that true and false they both take two inputs, right? We'll just call them x and y for now. We don't know exactly what this x and y is, but we know that it does take the x and y. So why don't we, well, rather than explaining so much, why don't you just see how it works, and then you could try to figure out how to come up with the next one. So why did I write true here? Because, well, I just thought about what happens if b is false, right? If b is false, then, well, I don't know what the x is, but I know that false selects the second things out of the two things that is given as inputs. It's going to select the second one. So I know that this looks more or less right? There should be true here. All right, but what if the b is true, right? What if the input is true, right? Then, well, it's going to select the first thing. In that case, x, well, that should be false, right? Because it should evaluate to false. Don't worry if the way I'm explaining this makes no sense. I actually really find it really hard to come up with these functions on your own. So any way that you could figure out a way to explain it to yourself, that would be nice. Do what you can, basically. That's what I'm trying to say, right? So now all there's left to do is test it, right? So we could test, right? There's only two possible things we could pass into it. Not false, it gives us true. Not true, it gives us false. How about this one? How about we do and, right? So I think you know how this works, right? Like true and false should give us false, right? It's like if I say, do I really need to explain this? I'm gonna just do it anyway. If I say my name is Ronald and my name is Tom, both of those things cannot be true, so the whole statement is false, because that's how and works, right? If I say this and that, I am saying that both of these things are true, not just one of these things are true, both. So this is how I'm going to do it, right? It is a function that takes two inputs. Yeah. Well, we can consider the first input, right? A. And if it's true, well, we'll go inside these parentheses, right? We'll go into, well, now we need to know if B is true. If B is true, then, well, I'll let it select true. And if it's false, then the result will be false. And now after this parentheses is what will happen is what A selects if it is false. And I'll just allow that to be false. So basically, if A is true, then we go in here and we ask, is B true? Then true. If it's false, then it selects false. And if A is not true, then it doesn't select this at all, but instead it selects false. So and true, true, that should be true. And oh my god. No, how did I must have pressed something random on my keyboard. And true, false, right? False, false, true. That's false, and then false, false. Obviously, that's false. a shorter way we can write this is, well, this right here, B true false, is redundant because it's going to tell me whatever B is, right? So if I say like true true false, that's going to give me true. If I say false true false, basically B is already a true or false thing, right? So if it's true, I don't need to convert it to true, and if it's false, I don't need to convert it to false. So I can replace this whole thing with B and test it, and it works, right? And true true and true false. I hope that doesn't keep happening. Okay, so yes, this made it shorter. Actually, what will make it shorter even more is changing the A, this false here, with yet another A. Why does that work? Because if A is false, well, it's just going to go ahead and select itself, which is false, which is what we need the result to be if it is false. Okay, so A, false, false, true, false, false, true, false, true, false, false, true, 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 right? So yes, it works. Okay, how about or? Can you think of a way to implement this one? Well, if A is true, then the result is true. If it's false, we need B to be true in order for it to be true. So if B is true, then it'll be true, but if it's false, it'll be false, right? And as you know, we have this is redundant, right? It's the same as just B. And actually, if A is true, we don't actually need to write true. We could just write A, and this will totally work, right? So we'll say and or true false, and that'll be true, or true true, that'll be true, or false true, and then finally or false false, that'll be false. Yeah. Same way we can do XOR. It's pretty easy. It's like saying not or, but just do it this way. A, B, and then if A is true, then we want not B. If not, then we want B, and that should work. All right, I just figured that we could probably do these first because it seemed like the simplest and the first thing you should probably try to implement in lambda calculus, even before numbers. And just for niceness sake, just for clean code sake and documentation sake, we will put the data type of the things that we're defining on top, right? So true and false are booleans. Not, it's a function that takes a bool and returns yet another bool. And then these are functions that take in bools. It takes in two actually, right? I'll just do it lowercase everywhere. Okay, yeah, it takes in because like I should not keep repeating that. You should have watched the video, but hopefully you did, because you would have learned about currying, and actually the fact that this right here is actually not a function that takes two inputs. All functions in lambda calculus only take one input and one argument. But if you have a function that takes an input and then it returns yet another function, then it kind of just acts the same exact way as a function that takes two inputs. It acts the same way, right? And if you saw the video, then you would have had this explanation, and you would be fine by now. And so anyways, that's the reason I'm writing it like this, right? It's actually because in reality it's a function that takes in a boolean and it returns yet another function that takes in a boolean, and then that function returns a boolean, right? So really, well, this is a way of saying it's a function that takes, the last thing is the actual output, right? The output after applying everything, right? So as input we take two booleans and the output is one boolean. That makes sense, right? And is a function that takes two booleans, returns a boolean. Okay. So let's see. Well, I guess we should talk about numbers, because I mean there's only so much we can do with booleans before we have to do something else. I think this is pretty much all we should do for now. So let's see, numbers, right? Arithmetic. How do we define them? It's going to be a function that takes two things and returns the first function applied, the first input applied to the second that many times. So look at this. Look at the number 2, right? It takes a s and a z, the first and the second, and it applies the first 2 times to the second thing, right? And notice the number 0. This is the number 0, right? It applies the first thing to the second thing 0 times, as you can see. So these are numbers, right? I actually like these more than the real numbers that we know about, like the 1, 2, 3, these symbols, because this is like more real actually, right? If you see 5, you learned that 5 objects, the grouping of 5 objects is the number 5 before you learned that the symbol means the number 5. Actually, I'm not really sure which one you learned first, but what I do know is that 5 objects grouped together means the number 5 more than this symbol right here, this 5, right? Like if some alien civilization, you know, creates numbers, they're probably not going to use this exact same symbol for 5, but whatever they do use as the number 5, they will mean it to mean 5 objects grouped together, right? So really, this is real base 1 numbers, right? We cannot deny the validity of these numbers, right? This is 1 object, these are 2 objects, these are 3 objects, right? One time that you see the first parameter in the body of the function, 2 times, 3 times, you get the idea. But the point is, we want to figure out the first thing we can do with numbers, right? So what's the first thing we learned how to do with numbers at all? Well, the first thing we learned how to do is count, right? And what's counting really? Counting is really addition by 1. So that's the first function that we will learn about numbers, addition by 1. Sadly, I don't really have a way to derive it, so I'll just show it. And I consider whoever thought of this to be a genius. But at least maybe in the naming of the variables is a way that I've figured out to kind of make sense of this function. So this is it right here. Also, just a side note, if you have a keen eye, you may have noticed that this function that is equal to the number 0 is actually the same as false, right? It's actually alpha equivalent. So here it is, right? 0, and you could actually say it's equal to AB dot B, right? Because of alpha equivalence. So let's just write down these numbers, right? That's what you want to do, right? Lambda AB dot AB, and then 2 is lambda AB dot A applied to AB, and then 3 is lambda AB dot A applied to B. All right. So I just given you a function here. By the way, I'm going to call these nats for natural numbers because that's what they are, right? Integers would be numbers like these, but that can be negative, right? So natural numbers are like integers, but you cannot go negative. So let's go ahead and use this function. Before I try to explain at all how it works, just look at that, right? It does actually, I would actually rather call it +1, but there's a reason I also want to call it plus. So anyways, I've called this function +1. Remember, 1 has no meaning in here. It's only a function I've defined, right? And +1 is a different function than 1, right? If I put also, if I take away space between the stuff, it's gonna mean something totally different. See, look, it doesn't mean anything. It's just plus 1 1. So we want to use spaces between our variable names here. Unlike here, where we only have a bunch of single letter variable names, in my interpreter we do want to use spaces between the names, because we could have names that are more than one letter, which will be really nice, as you'll see, for clarity. So we're noticing here that the function is taking as input a number, and it's giving me the next number. What the heck? How is it working? Does it work for other numbers? 0 turns into 1, 1 turns into 2, 2 turns into 3. Oh my god, this is magic. Alright. This is the kind of thing that makes me watch the other lambda calculus videos, to try to see if other people have neat ways to explaining it. One of the ways that I've seen is that well, this n is for number, right? So let's just think about what happens when we apply this function to, let's say, a 1, right? So I've chosen n for number, right? And so when I apply this function to a 1, the n is going to be replaced with the number, right? So here it is, n gets replaced with 1, right? Okay, and now notice this. Now what we have, it's not simplified or reduced yet, but just notice that we have a function here that takes 2 inputs. So it's already kind of in the form that functions are, that numbers are, right? All the numbers seem to be functions of the form function that takes 2 inputs, right? And so now let's expand 1. It's going to be this lambda ab dot ab. Well, really, actually, I don't need to actually do all these reduction steps by hand. I could just actually turn on the reduction steps and we can look at them. Alright. Oh, well, I actually turned them off. Okay. So, yeah, plus 1 gets replaced with the successor function. That's what it is. That's another name that they gave it when this was invented. Oh, looks like I deleted it. Equals lambda nfx dot fx. Right. Okay. So yes, it gets replaced with that, and then it does the reduction kind of fast, actually. I don't know exactly why. I did a lot of stuff to optimize, and I'm not gonna look at that right now. It's not crucial for the video. So what I will say is that all these numbers are the first thing applied to the second thing that many times. I actually just it wasn't something wrong with the reduction steps. It was just that I didn't write out the whole function correctly. That's what happened. So yeah, you can take a look at that, see how it reduces. But what I like to say about it is that okay, we have this function applied to the A applied to B n times, right? So what we're doing here, okay, actually let's look at this function. Okay. Alright, I know I've gone like so many minutes. How many minutes? Maybe 38 minutes without mentioning, because of course you should have watched a video about lambda calculus before continuing to watch this video, but I should have mentioned, or maybe not, that this is the simplest function in the lambda calculus. It just takes a single input and returns it, right? And so we call this ID, the identity function. And what does it do? It just returns the output, right? So what's the ID of 2? Well, just 2, right? And so why did I bring that up? Because let's look at this function now. of a similar function to the addition by one function, but just a little different. It's just gonna kind of mirror the inputs, right? So it takes an n and an f and an x, and it returns n and an f and an x. And I'm actually gonna call this id2. And what happens if I apply it to a number? I actually just get the same number back, right? So how we want to look, why I showed this is because what's the difference between this and the plus one function? Well, look at this. We just have an extra f around it. We're applying the function just one more time, and that really is what makes the difference between this number 2 and the next number 3, right? It's just that in the body of the function, we have the first thing applied one more time to whatever we had, right? So we have this f right here, just an extra time. And I guess that is why it works, or at least my interpretation kind of why it works. So alright, that's our first useful function on the natural numbers, right? It just takes a natural number and it gives you the next one. So now that we have this, real quick, we're going to want to implement all the numbers. Not all of them, because there's infinitely many, but at least 20, because that'll be something that makes sense. So rather, I'm just going to do something really lazy real quick and just generate them with JavaScript. Let me just think about it real quick. So I want to generate 20 numbers, so I'll do array 21, because it's from 0 to 20. Array 21 dot fill dot map. Alright, and I want to get just index. I just want to create I'm just going to create lambda calculus code real quick dynamically. So what I want to get is, what I want it to be is something, and I'm going to join it with a new line, and what I want it to be is a string, which is going to be the index, and then it's going to say equals to, and then, well, actually I'm not going to do it for 0, so actually it will be array 20. Alright, and it's going to be the I plus 1 equals to, and we'll do that plus 1, right, my plus 1 function, and I'll do it to I, and let's see what this gives me. And I think this is it. Yep, this is what I wanted. I'm not sure which one is faster. I think I could have done it faster by hand, but whatever. So this will give me the first 20 natural numbers, I think, right? We could test it right away, because we're now going to implement the addition function, right? Alright, I'm going to do something a little weird. I hope you guys don't mind. Hopefully I don't get too much criticism for this, but just because I can, I'm going to make it an infix function. It's pretty much going to be the only infix operator in all of lambda calculus, but just because it can be done, why not? This is my flavor. This is my code, my video. I get to do what I want. So actually, let me just show you that this is going to be the same as that, right? I'm actually just renaming the plus 1 function. Alright, why? Because just take a look at this neat little thing and pause the video and try to see if you could figure out why this is the case. How come I can do this? Look at this. 4, it's really, all I'm doing is 4 plus 1, 3, right? Maybe that will help you realize what is going on, right? Maybe test it out a couple more. 0 plus 3, 0 plus 0, 10 plus 10, 7 plus 12, 8 plus 12, 9 plus 12. Now this is, oh, look at this. Now this is 21, but we don't have it defined, so we can't really see in a nice way what it is. Or rather, we're looking at like the raw function form of it. So why does it work? Because what happens with numbers, right? What are numbers really? Numbers are really functions which are that many times applied, that apply the first argument to the second that many times, right? So if we do the call plus 3 plus 1 2, what's really happening? 3 is actually AB dot A B, right? And we apply that to plus 1 and then to 2, right? So what happens is plus 1 gets replaced with A. I'll just do it down here, right? Plus 1 gets replaced with A. And then B gets replaced with 2. So now take a look at this. We're actually applying, we're doing plus 1 to 2, and we know what that is, 3. And then we know what plus 1 to 3 is, it's 4. And then plus 1 to 4 is 5. So now it should make a little bit more sense, right? First we do plus 1 to 2, and that is 3. And then we do it to 3, we get 4. Do it again, we get 5. So we are really just doing iterative counting. Yeah, that's how this addition is working, right? It's like it's taking counting. It's taking our counting, which we just figured out how to do, and it's saying if we count x many times on y, then we're doing x plus y. Okay, so that is addition. Let's see, are we anywhere close to? We're not close yet to doing this questions. We'll get there. Almost there. Okay. Multiplication. How does it work? You really should just read this paper, because these first few things are kind of hard to come up with yourself, and they just give it to you. And then here, using what we know and what we've learned, it becomes a little easier to answer these questions. And these questions are the real main goal of the video. So we should probably focus more on these, but we'll still go over how we can come up with multiplication. Pause the video and try it yourself. Okay, hopefully you've already done that. Here's a way you can do it. Lambda AB dot it's actually ABF dot A, and then we apply that to BF. Does it work? Let's test it out. 3 multiply 3 4, we get 12. 3 5, we get 15. 3 0, we get 0. 0 0, we get 0. 3, we get. I'm pretty convinced it works. All right. So now, well, we know multiplication from grade school is just iterative counting, right? So if we multiply 3 times 2, we know it's going to be either one of these. It's going to be either 3 plus 3 plus 3 or 2 plus 2 plus 3. Yeah, actually 3 plus 3 or 2 plus 2 plus 2, right? Which one of those? You might want to try to figure out which one it is. So, maybe it'd be easier to see if we just put an X here at the end. Alright? So we still get the same results. It still works. Now, but I think an explanation for it might just be a little easier. Alright, so we know a is a number, right? It's going to be one of the numbers that we're multiplying, a times b. And okay, well, let's just say we're doing 3 times 2. A is 3, right? Which is really lambda a b dot a b. And we apply that to bf and to x. So really, a is going to be replaced with bf. X is going to be, b is going to be replaced with x. And so we do bf, and then instead of b we write x. Well then, look at this. We've repeated 3 times something. We've repeated something 3 times. So now we can go back to this question. Are we doing more of 3 plus 3 plus 3? I mean 3 plus 3, or are we doing more of 2 plus 2 plus 2, right? Alright. Well, here I actually am seeing 3 things repeated. A is 3, and so we're actually doing more of this one. 2 plus 2 plus 2, right? B would be 2 in this case. And I guess all of these get added together. How can that make sense? Okay, well, let's just go in here and reduce, right? 2, if these parentheses are actually not needed, not necessary, because of left order application, so that could be removed. 2 applied to f applied to x would actually give us f x, right? And there we have 2 so far, and then we have 2 apply. Now let's look at here. We have another 2 here, right? We could remove those parentheses. We have 2 applied to f applied to this stuff, so we know that's going to be f and then all this stuff. And we have yet again another 2 here. Well, we have 2 applied to f, and then the result of that all applied to this stuff. We already kind of know what's going to happen. It's going to be like f and all this stuff. And now take a look. We actually have 6 f's here applied to an x. I mean, well, all we need is the lambda x on outside. This is the number 6. Oh, I have to comment out that stuff. Yeah, this is the number 6. It's not showing us because probably it thinks it's oh, well, no, it's not. I need an f, of course, in the front, and there we go. Now it is the same as the number 6. Yeah, hopefully that was kind of enough to see the general idea that it works, right? Kind of trying to demystify the magic. But the real sad truth is that I didn't derive it myself, just so you know. So if hopefully you don't have your video paused and you're stuck there forever and ever, because that's what I told you to do, to try to figure it out. Hopefully you don't do that, because I didn't do that for multiplication. And so don't feel bad about not figuring it out if you didn't, because I didn't. So anyways, we have 2 things. Just really important, make sure you don't try to do addition like this. In fact, I'm going to tell you to open another tab, because if you do that, you probably time out, because what you'd be doing here is actually exponents, right? Here I'll show you, right? This will actually be, here, I'll do this. This will actually be 3 to the power 2, which is 9 if we try to evaluate this. Not going to be 4. It's going to be 9. Why? Because plus 1 is 2, and if I actually do this, 2, 3, it's actually going to give me 3 to the power 2. So yes, another fact about another operator that we can use now, which would be exponents. I guess I can do it like that. And so, yeah, really simple. We just reverse the two things, and that will give us the power. How do I know that? Simply because of, I think they told us this right here. Either they told us or I learned it from somewhere else, but I definitely didn't come up with it on my own. If I were to try to do it on my own, I probably would use like recursion and iterative multiplication. But anyways, somehow I know it, and now you know it too. These are not the ones that I'm asking you to try and solve on your own. But if you can, if you want to, you can. So let's test it out. So 2, 3, give you 8. 2 to the power 4, 16. 3 to the 3. Anything to the 0 will give us. Actually, that is an unexpected result. Because I learned that anything to the power 0 is supposed to give you 1. So I actually haven't tried with 0, so I didn't expect to see ID. I expected to see 1 because anything to the power 0 is 1, but seems to not be the case right here. So weird. I'm gonna look that up real quick. So yeah, to the power 1, anything is the same thing. 4 to the power 2. That's so weird. Okay, lambda calculus 0 to the power. Wait. To the power 0. Oh, someone said 0 to the power 0. Yeah, so gives the answer 0. Oh, well, I guess that this person is using an encoding where it gives the answer 0, but I'm using an encoding where it gives ID. Does anybody know an encoding where the answer is 1? No, it gives 1 as the answer. Wow, well, well, this is actually true, right? It does give 1 as the answer. If you 0 to the power 0 gives you 0, then you don't really have power implemented, and I guess I don't either. Strange, but for the most part I guess I do. And even if I don't, it is totally fine because I actually don't need exponents at all. We don't need exponents at all for any of these things that we're doing. So don't worry about this right here. Yeah, and we're not gonna go into this right now. Okay, so we'll just say that this is the operator that gives exponents except to the power 0. It won't work for that. So what else? So I think that's pretty much enough for building things, right? For going up, right? Making numbers bigger. How about making numbers smaller? How can we subtract by 1 in the lambda calculus? I'll show you real quick, but please, maybe don't pause the video. Don't pause the video, because it is one of those things that definitely seems more tricky to derive. So, okay, once we do this, we'll obtain subtraction. And yeah, once we can count backwards, right? Remove from a number. Oh, well, I just realized the camera was a little messed up. Okay, once we can subtract numbers, we can, once we can count backwards, we can subtract numbers, right? And then once we could subtract numbers, we could figure out how to do less than or greater than. But okay, so what I'm going to do actually is break this video into 2 parts, since it's pretty much been an hour, and I don't think people like watching extremely long videos. So what I'll tell you to do from this point on is watch the next video. But first we'll do the implementation of the predecessor function, which subtracts a number by 1. So let us get on and do that. We're going to need a couple functions. We're going to need this strange miscellaneous function. Actually, well, before we use that function, we're going to need pairs. So maybe if you want, pause the video and try to figure out how to implement it yourself. But this is how it works. It's gonna accept two things, two elements, and just give us the pair. I guess these are all. I'm gonna go with the convention of capitalizing all the data types, just because I noticed that nat was capitalized. Alright, so yeah, so how does it work? Really simple. It takes an A and a B, and then at the end, in order to select one of these two things, it's going to take I'll just call it select, and then this is the result, select A, B. Okay, I didn't really explain anything, but this is how it works. Pair, let's make a pair of X and Y, right? And I'll just call this P, right? And how do I get the first thing out? Well, I could say pair true, right? And then when I do this, true, well, select gets replaced with true, and then the true will select the first thing. In this case, it's X. And if I feed it a false, then it's gonna give me the second thing. All right. So we could actually implement these as functions, even though it was pretty simple. I think this will be even more clear, right? So first, it's a function that takes a pair, and I'll just call it P, and it gives me pair true, but this gives me the first element of the list. Second, right? It takes a pair, and it gives me the second element of the list by applying the pair to a false. And these functions are of type pair, and they return some expression, E for expression. Alright, so let's test it out. So my pair will be, I don't know, a pair of 1 and 2, right? And I want to get the first of this pair. So the first of that pair will be 1, and then the second of the pair will be 2. Okay, so there it is, pairs, right? Now, why did we need pairs? Because we obviously want to do a function with pairs. It's going to be a function that takes a pair and it returns yet another pair. The pair that it takes is going to be some pair AB. Actually, this function could be called like transform or something, but I'm going to actually call the function specifically what it does, which would be taking a pair A and B, AB, and it gives you a pair consisting of the second of the pair and 1 plus the second of the pair. Okay? And alright, so we have that function now. Well, that's actually the name of the function, but the name of it nicely describes what it does, so now I could easily write it. So it takes the pair, right, and it constructs a whole new pair. You could pause the video and try to finish this yourself if you want, and because I feel like maybe there's enough information for that. So it takes a pair and it constructs a whole new pair consisting of the second of the old pair and 1 plus the second of the old pair. Okay? So if we have a pair 0, 0, and I apply this function, I gave it kind of a long weird name, but it really describes what it does. And I apply this to the pair 0, 0, I actually should get the pair, I'll just call this 0, 1, 0, 0, right? and it should give me the pair 0, 1, right? So pair 0, 1. Okay. Remember, the only symbols that actually make any sense in this lambda calculus is the lambda symbol, the dot, and parentheses. Everything else can be considered as part of a variable name. So let's apply it, and there we go. We get the pair 0, 1. Okay. We know that it works. If we do it again, we'll probably get another pair, but in this time it's as like a lambda. And gonna just shorten this to S because you already know that it selects. Okay. So we have the function. Now what? Now we kind of have enough to implement the predecessor function, which is subtraction by 1. Alright, so might want to pause the video, try to implement it yourself, but here we go. It takes in a number, and then what it does, it simply returns the first of a pair, right? Well, that's what we use the FST function on. We use it on a pair, right? So this will be a pair, right? And the pair that it'll be is the pair that we get when we apply n times the function I just made up, the transform function, n times the transform function. I'll just put an extra little space here just for clarity. So n times the transform function to the pair 0, 0. Alright, so why does this work? Well, okay, just first of all, remember that numbers will do this, right? If I give a number 2 arguments, it will apply the first one to the second one that many times, as you know. Alright? So just remember, we applied it one time to the pair 0, 0, right? And what did we get? We get the pair 0, 1, right? And if we get the first of this pair, remember 1, right? We applied it one time, so it's actually important to note the number of times we're applying it, which is 1. So we apply it one time to the pair 0, 0, and then we get the first of that, and then look what we get. We get 0, actually. So that is the number before 1, isn't it? If we apply it twice to the pair 0, 0, and we get the first of that, and we get 1, which is the number before 2. So I think now with enough confidence we can test it and see that it does indeed give us the number before the predecessor function. Yes. So now here's something you can guess about. What will happen if we apply it to 0? Alright, well, all we have to do is follow the logic. N is going to be replaced with 0, right? That's what n is at this moment. It is 0. And what does the function 0 do? It applies 0 times the first one to the second one. So in other words, it takes the two things and it just gives you the second one. So what's going to happen? N is going to be applied to this, and it's going to be applied to pair 0, 0, and it's just going to give us 0, 0, and then we select the first of that. So the predecessor of 0 is 0. And well, I think that about wraps it up for this section of the lecture, and we'll continue real soon, and we'll start doing these 11 questions. See you soon.